We're going to take a look at a few more examples of going through and solving these polynomial inequalities. And so we have this one, 2x squared plus x greater than 15. First step is to make sure that we have 0 on one side and then all the other terms to the other. And so we're just going to subtract 15 from both sides to get 2x squared plus x minus 15 greater than 0. Then what we're going to do is we're going to solve and find the zeros of the polynomial. Okay, and those are going to give us our boundary values. So factoring this, we need a 2x and an x. And then to get a 15, we're probably going to need a 3 and a 2, or 3 and a 5, excuse me. And let's put the 5 here and the 3 here. And we need a positive. So I think if we put a positive and a negative here, this is going to give us negative 5x. And this is going to give us 6x. And 6 minus 5 gives us the x in the middle. So it looks like that's going to be the correct factorization. Okay, just reminding folks how to go through and try to factor that. And then we set this equal to 0. And then we just set both of these factors to 0. So 2x minus 5 equals 0, and then x plus 3 equals 0. This one gives us x equals negative 3. That's pretty easy. Over here, we add 5. We divide by 2. And we get that x is equal to 5 halves. Okay, so those are our boundary values. Now notice that we have a greater than. Okay, so we construct a number line to get our intervals for this. We should have an open circle at the boundary points. Okay, so we have a negative 3. Whatever our solution is, it should not include negative 3. Okay, because it's going to be greater than. And then also we have 5 halves, and there should be an open circle there. So for our 3 intervals for this, we should have from negative infinity to negative 3, not including, and then from negative 3 to 5 halves, again, not including, and then finally, we would have from 5 halves to infinity. And so now what we're going to do is we are going to pick some test values. Okay, so we have our intervals. And remember, our intervals were from negative infinity to negative 3, and then from negative 3 to 5 halves, and then finally from 5 halves to infinity. Right? Then we need test values. Okay? So some test values, we certainly know that negative 4 is going to be a number between negative infinity and negative 3. We always pick 0 whenever we can. And then 5 halves is 2.5, so let's just pick 3 for the other test value. Now what we're going to do is we're going to substitute back into our equation, okay, or I'm sorry, an inequality. Now, what I like to do is I like to substitute the factored form, okay, or substitute into the factored form. So we have 2x minus 5, and then x plus 3 greater than 0, okay? And let's see what happens when we substitute back in for x. So this is going to be 2 times negative 4 minus 5 times negative 4 plus 3. And if we simplify that, that's going to give us a negative 8 minus 5, which is negative 13. And this is going to give us a negative 1. So we get 13 greater than 0. And that's a valid statement. Okay, so remember our last column from the last video, we have in or out. So this is in the solution set. Okay, so this is part of our solution set. Let's see if we substitute 0, what happens. So we have 2 times 0 minus 5 times 0 plus 3 greater than 0. And so this becomes negative 5 times 3, or negative 15 greater than 0. And that's certainly not valid. Okay, so this one's out. Okay, so that's not part of the solution set. Now let's try 3. So we would have 2 times 3 minus 5 times 3 plus 3 greater than 0. 2 times 3 is 6. 6 minus 5 is going to be 1. All right, so that's going to be 6 minus 5 times 6. So that's 1 times 6, which is going to be 6, which is greater than 0. So that's in. So we have 2 intervals that are part of the solution set. And those 2 intervals are going to be x is an element of negative infinity to negative 3 union 5 halves, comma, infinity. All right. Now, the two examples we've done so far are pretty straightforward. Okay. Let's take a look at one that's a little bit sneaky, but actually a little bit easier than the previous one. So we have this x squared minus 8x plus 16 greater than or equal to 0. All right. So first thing we do is we set it to 0. Done. Next thing we do is we take the polynomial and we try to set it to 0 to find our boundary values. Okay. So we're going to factor it. If I factor this, we know that the two numbers that multiply to be 16 are 4 and 4, and to add up to -8, we need a negative and a negative. So we get x minus 4 greater than or equal to 0, or x minus 4 squared is greater than or equal to 0. So that means that our boundary value, we only have 1, because if we solve this, we set x minus 4 square equal to 0. If we take the square root of both sides, x minus 4 is equal to 0. And that means x equals 4 is our only boundary point. And it includes it because we have the greater than or equal to. Okay, so if I draw my number line, here's 0, and then here's 4. And so in the other the other examples, we had 3 intervals. In this one, we're only going to have 2. We have from -infinity to 4 inclusive, and then we have from 4 to infinity. Okay, so remember, this is like our boundary value. It separates. Okay, and so we're going to go ahead. We're going to have our intervals. Okay, so remember, -infinity to 4, and then from 4 to infinity. We're going to have some test values, and that's pretty easy. Again, 0 if we can, and then I'm just going to use 5 because 5 is nice and easy. And then again, I like to use the factor form. So we're going to have x minus 4 squared greater than or equal to 0. So x minus 4 squared greater than or equal to 0. And then let's just substitute our boundary values back into there. Okay, so let's see which ones work and which ones don't, if any of them. Okay, so if I substitute 0 back in, I get 0 minus 4 squared greater than or equal to 0. All right, and that's going to give us 16 greater than or equal to 0. Okay, so that's in. So in or out, and this is going to be in. All right, so this is part of the solution set. And then over here, we substitute 5. 5 minus 4 squared greater than or equal to 0. 5 minus 4 is 1. 1 squared is 1. 1 greater than or equal to 0. That is also in. All right. So it looks like that the entire number line is going to be in, okay? Because remember, 4 is included, okay? So that means no matter what number we plug in to this inequality, it's going to be greater than or equal to 0, okay? And if you don't believe me, just start plugging in some numbers. You could also graph the function, and you could see that no matter what, it's going to be above the y-axis or above the x-axis. In fact, let me do that. So we have y equals x squared minus 8x plus 16. And notice what happens. It touches the axis at 4, and then it turns around, likely because it has a multiplicity of 2 right here. Okay, so remember we talked about multiplicity for polynomials. So that means that no matter what, this function is always going to be greater than or equal to 0. Okay, so for our solution set, x would be an element from -infinity to infinity. All right, now let's say for some reason we change this to just greater than 0. Okay, so if we were to go through and just change this, then what would happen is, all right, and this, by the way, this is the answer for what we had, but let's say we had x squared minus 8x plus 16 is greater than 0. Well, then 4 would not be included. And so our solution set would be -infinity to 4, union 4 to infinity. All right, so just making sure that we understand that, this sign, or if this is not underlined, that would change what happens with our inequality. All right, so we have one more example of this, and then we're going to move on to rational inequalities in the next series of videos.